Let's see this played out through an example. We have the vector a, negative 2, 3, 1. We know that we need its length several times in the calculations. So that'll be the square root of negative 2 squared plus 3 squared plus 1 squared. 4, 9, and 1 is 14. All right, so that's our length. And so what we would have as our formula, if we're looking first for the scalar projection, that is the component of b in the direction of a. And a little side note, that's a scalar value. It's a length. That is simply equal to the a vector over its own magnitude dotted with the b vector. Well, we have all the ingredients here. We can take a dotted with b, negative 2 times 1, or b dotted with a, the order doesn't matter. Negative 2 times 1 is negative 2, plus 3 times 1 plus 2, all over the length of a, square root of 14. And that gives us, cancel, 3 over the square root of 14, or around 0.802. And that would be whatever the a vector here is. We would have found that projection of b, keeping consistent with our colors here. That was our b vector, and we projected, we would have found that this v vector, when projected down here, gives a length of 0.802 units along the a vector. All right, so that's the first step. Then we can talk about the vector projection. So what's the actual vector that is represented here? Well, we can compute that on the next page. The projection of the b vector onto the a vector, which is a vector quantity, is equal to what we just found, the length, times the unit vector in the a direction. And we found this already, that was our component. Let's use the actual symbols. We had 3 over root 14. And then the unit vector in the a direction is the a vector over the length of a. And so we get 3 over root 14 times the a vector itself, negative 2, 3, 1, scaled by its length, square root of 14. And then after that, this is totally fine. But if we want, we can tidy that up a little bit. Notice that we have 2 root 14s in the denominator. We can leave this scalar times a vector as the form for our projection. Notice we have the direction very clearly in the same direction as a, but all we've done is scale it. And that matches the diagram we have here. We've got the a vector, and all we're taking is some portion of that, some scaled multiple of that, and that's the fraction we're multiplying by.